Yeah, good morning, everyone. You have to attempt the quiz, online quiz. You have to go to the Greatscope, log in with Triple IT account, and do this quiz.
हम आपका नेट नहीं चल रहा। अम्मा नेट नहीं चल रहा आपका।
Hello, please turn off your microphone. Please turn off your microphone. Okay, so let us continue with the lecture. Good morning to everyone. This is lecture 19, and turn off your microphones. So we will do today continuous random variables, and then we will also discuss probability density functions. We have seen PMF, and then we have seen CDF, and then there is something called, so we have seen PMF, we have seen CDF, and then there is something called PDF. Okay, so these are the three things that that you need to recall. Okay, so last time we were doing continuous random variable. That's where we left, and what we said is the following: a random variable x with CDF, the cumulative distribution function, which is denoted by capital F here, is said to be continuous if fxx is a continuous function for all x in R. If the CDF of a random variable is continuous, then we declare the random variable to be continuous. So the few things to note are CDF is always a continuous function, whereas PMF may not be continuous. Okay, so we are talking about the so CDF will always be continuous function even for the discrete case. Okay, so the point here is like even for the discrete case. So it's like even for, oh, okay. No, sorry. Oh no, it cannot be for discrete, right? I'm sorry. So we are talking about continuous. Okay. So CDF will be continuous for the continuous. I mean, if the random variable is a continuous random variable, and the discrete case, we have seen that CDF may not be continuous because there are jumps, right? So we have jumps here. So these are not continuous. Okay. So it excludes the endpoint and then it takes from here. So, but CDF in the case of continuous random variable will always be like it's continuous. Okay, in the case of continuous random variable, but that's the way we define anyway. We will usually assume that CDF of a continuous random variable is differentiable. I will point out this this more precisely what I mean, because there are cases where endpoints you may not worry about differentiability. Okay, so in general you will assume that CDF is differentiable. In general we will assume. Okay, but there will be cases where it won't be. So this is just an assumption part here, and although the PMF does not make sense for continuous random variable, we define probability density function. So PMF doesn't make sense for continuous random variable. We have seen that because pointwise values such as probability that x is equal to let us say some point, right? So E may not make sense for continuous random variable because it may turn out to be always 0. Okay, so this PMF does not make sense usually. Okay, so for continuous random variable, but we can define something called PDF, the probability density function for a continuous random variable. Okay, so that's the that will play the role of PMF in the continuous case. Okay, so we will see what it means. So probability density function, or in short, it's called PDF, would be defined as probability per unit length. So it's like instantaneous probabilities you can define, just like you have instantaneous slope or the derivative that you define for a given function f, you have the corresponding derivative of the function. So that in a similar way, we will define a probability density function, because PMF cannot be defined. So we are looking for something similar to PMF. For a continuous random variable, we define the PDF. Okay, so this is the PDF as follows. So this will be defined as a limiting process. So limit delta tends to 0. Delta is some number. Okay, or you could have taken epsilon here. So we define it as probability per unit length. Okay, so in other words, we take some small neighborhood so it's like x in some neighborhood between x and x plus epsilon. Okay, so x is lying in some let us say some small enough interval. This is small enough because delta is tending to 0. Okay, so this interval delta, you can write delta here. Okay, so here delta tends to 0, right? So this will be like you are computing a instantaneous probability in some sense. Okay, so by taking the ratio, and it's a probability per unit length. Okay, so instantaneous probability per unit length, you can think of this like that. So we define PDF to be like this. Okay, so the ratio of the probability in a small enough for a small enough interval, okay, let us say, and divided by that interval. Okay, so that's the probability density function. So here fxx is the probability density at point x. So this is at point x. Okay, now we recall that probability that x less than equal to x plus delta can be written like this. Remember, initially we wrote a result where we had less than equal to b, and that was equal to fx b minus fx a. So we are using this result here. Okay, so we have seen this before, and so similarly here a you can take x and b you can take x plus delta, and this will be fx of b, which is x plus delta, minus fx a, which is x here. Okay, so we know this. So we know that the numerator can be replaced by this fx x plus delta minus fx x. So fxx now can be defined as fxx plus delta minus fxx. Okay, so we have basically substituted this here by using this result here. So so now we know that this is of the form, remember in calculus we had a limit, let us say epsilon tends to 0, and we had x plus epsilon minus fx by epsilon. Okay, and this was defined to be the derivative of f at x, or in other words we write this as df by dx. Okay, so this is how we define the derivative. So this is like recall calculus. Okay, so this so using that we can also write like this, but this is the derivative of the CDF. So this is nothing but CDF, right? So PDF is nothing but derivative of the CDF. If you want to find a PDF at point x, then you take the derivative of CDF at point x. Okay, so that's what it means here. Okay, and now we can formally define PDF. So let x be a continuous random variable with continuous CDF. So it is always there, and the function fxx defined by this way. Okay, so fxx is derivative of the CDF, or sometimes the derivative is denoted by this, right? So it's called the probability density function of x. We assume that fxx is differentiable. We will assume that that fx, the CDF, is differentiable. There are cases where it's not differentiable, we know that, but we assume that because only then we will be able to do this, right? The derivative, and we can derive the the PDF. Okay, so that's why the assumption. Okay, so example of CDF and PDF for continuous random variable. Let x be a continuous random variable, and x denote the real number chosen uniformly at random. And here, so this is an example that I discussed in the previous class also. So here, so we will choose a number uniformly at random. Okay. So we know that CDF of this case is given by this. So this is something we derived in the last class. And this happens to be uniform distribution. Okay, so this we call it uniform. So just like in the discrete case, we had various distributions, and we also had uniform distribution. Okay, for instance, if you roll a die and the outcomes are the 6 possible outcomes, and then probability at each of these was 1/6. Okay, so those were examples of a uniform. Okay, so and in this case, this will be called uniform. So in the interval AB. Okay, so that's how. So in some, so I have already defined a uniform distribution for you here. Okay, the parameters A and B correspond to the to this. Okay, so usually sometimes you will see people write uniform 0, 1. This, and then if you put 0, 1, then you in place of x, I mean in place of A and B you put 0, 1. So in that case fx x will be 0 for x less than a, and this is x minus a 0, right? And b minus a is 1. Okay, so this is just x for a less than equal to x less than equal to b, and this is for x greater than 1 is 1, greater than 1. So like in this case it's like 0 and then 1, and this is was 0, right? So this is uniform 0, 1. Okay, so you can get uniform for by depending on which parameter you take. Okay, so it's uniform in the sense like it's like constantly it's increasing with a constant rate, right? So it tells you that the probability probability is like equal. Okay, so the jumps are like uh, um, are like uniform. Okay, so so if this would have been the PMF of let us say so in the discrete case it's like 1/6 1/6 1/6. So we get a stepwise function there. Okay, it's because that is discrete. So in the discrete case it will look like this, right? Until it hits 1. Okay, but in the continuous analog we see that it is like this. So so you can think like this. Okay, so it's not staircase, but it's a constant. So at each in a equal size interval you will see that the probability and the height is the same. Okay, so here and the height is the same. Okay, so that's how why it's uniform. Okay, so there is it's a continuous analog of the uniform case. Okay, so remember that in the continuous case, it doesn't really matter whether I use less or less than equal to. Okay, so in the continuous case, it really doesn't matter, because in the interval, if I say in the uniform case, if I do this, then probability that I compute, let us say between, let us say 0.5 and 0.7. Okay, so the probability that my x belongs to closed 0.5, 0.7, or it belongs to open 0.5 and 0.7, it doesn't really change my probability. Okay, it doesn't really change my probability because endpoints, single points doesn't really matter in the continuous case. Okay, so that's why you will see that the probability that x less than 2 is actually same as probability that x is less than equal to 2. Okay, in the so in the continuous case this doesn't matter, but in the discrete case it did matter, because in the discrete case we had a staircase. Okay, so if you include one here, then this is the probability that x is less than equal to 1 is different than probability that x is less than 1, because probability that x is less than 1 will sum up only this height. Okay, but if I take probability that x is less than equal to 1, then it will be like including this height. Okay, so there is a big difference. If you say probability less than 1, then it's only this much. If I say probability less than equal to 1, since because there's a sudden jump here, so this will be also included. So there will be a big difference between this and this. It's not equal in discrete case. In discrete case, it's not equal. Okay, but in a continuous case, there is no such jump like this, right? So in the continuous case, if we look at the CDF, it will be some let us say some curve like this, right? So it doesn't matter whether I take a so this is so it doesn't matter whether I take, let us say 2 is here. So so the height is this, right? So x less than equal to 2 height is this, and x less than 2 height is also this, because there was no sudden jump here. X less than 2 is still almost starting from here, and then x equals to 2 is also starting from here. So these heights remain same for x less than 2. Less than 2 is same as probability that x less than equal to 2. Okay, so it really doesn't matter because height is the same, because in the continuous case, in other words, like the length of open interval and this closed interval are the same. Okay, so if you see in that way, the measure, earlier I talked about measure. Okay, so the measure or the length of these intervals are the same, because single point measure is 0, right? So although you have 0.5 and 0.7 additional points here, but singleton points you can always throw out. Okay, so this will not change the length of these. So that's what it's trying to say here. In the continuous case, it doesn't matter. So if I want to get a PDF from the CDF, okay, then what I will do is that I will differentiate. So if I will differentiate, these guys are anyway 0. So this is where I have to be a bit careful, because what I'm saying is like the function is like this, and then this x minus a, b minus a. Let us say a and b are 0 and 1 for simplicity. So this is my a and this is my b. So this goes like a line, and then it flattens out. It should be flat. Okay, so this flattens out at 1. Okay, so so if I take a derivative, then you may immediately tell me that that derivative does not exist here. Okay, why derivative does not exist here? Can you tell me why derivative does not exist here? I claim that the derivative does not exist at 0. So derivative does not exist. Derivative does not exist at x equals to 0 and x equals to 1. Why? So can you tell me why the derivative does not exist? Yeah, no limit, but can you be precise? Is it? Yeah, it's a corner point, but what is the problem with the corner point? Yeah, left hand limit is not the same as right hand limit. Okay, that's got it. Okay, so so left hand limit is not same as right hand limit, right? So what do we mean? Like if we go from here, okay, so if we go from here, the slope it will tend to like 0, and if you come from here, from the right side, then the slope will be 1. Okay, so if you take the limit from this way, in other words, like the way you are taking the limit is like f of x. So if you go from this way, then this will be fx minus fx minus epsilon by epsilon. So limit epsilon tends to 0. So this will be the limit when you go from the left, from the left, right? And then you will have also limit where fx. Okay, let me do it. Okay, here. So fx plus epsilon minus fx by epsilon. Okay, so this is your right hand limit, and limit epsilon tends to 0, and then you can have the left hand limit, which is x minus epsilon. Okay, or like another way to say is like you do this you are tending to 0 from the positive side, and then I can also define limit epsilon tends to 0 minus. Okay, so it's like epsilon is negative and it's tending to 0. So epsilon is tending to 0 from this way, and here is epsilon is tending to 0 from the positive values. Okay, so if you take these, then they are not equal. Okay, so if you do this, then they are not equal. So and then you can check this for as an exercise. You can check that if you go if this left hand derivative f of x plus epsilon minus f of x by epsilon. Remember that epsilon is negative and then it's tending to 0 from the negative side, and here epsilon is positive and it's tending to 0 from the right side, and this will be 0 and this will be 1. Okay, so hence the derivative won't exist. Same point, same thing here. In this case, the right hand will be 0 and left hand will be 1. So again, it's not equal, so hence the derivative does not exist. But as I said, endpoints we don't care. Okay, endpoints we don't care in this case because those are like useless anyway. So we will go ahead and still go ahead and do the derivative. Okay, at the places where it makes sense. Okay, that's the point. So at the places where it makes sense, we will say, okay, let us do derivative. At least it exists at these points, and for corner points, we just make it keep it 0. Okay, so we keep it 0 at this point. So with this facts in mind, we can go ahead and still define the PDF. Remember, PDF requires derivative, right? And we know that derivative exists only in these points. I mean, derivative exists at all the points except for x equals to a and x equals to b, because those were the corner points. Okay, but these corner points are not really needed in our case, so we exclude those. Okay, and this and for including those corner points, we can just define it to be like 0. Okay, so this is like this: x less than equal to a, greater than equal to b. So this is the way we will work with PDF. Okay, there will be corner points. In many cases, there will be corner points, and beyond that, we will just define it to be 0, the PDF to be 0, because beyond those, it's anyway either constant or 0. So we will define it to be, if 0, it's anyway derivative is 0. If it is 1, beyond certain point, it will be 1. So that also derivative, we will define it to be 0. Okay, and we will consider derivative of the internal one. So this is the derivative of this. Okay, so if I take a derivative of this with respect to x, then I get 1 by b minus a. Okay, so this is the PDF plot of the PDF that I have here. Okay, so this is the plot of the PDF, and this is how it looks like. So now you can relate this to the PDF of, so relate this to PMF in discrete case. Okay, so in discrete case, remember in the discrete case, the PMF values for a, let us say, roll of a die. Okay, so this is 1, 2, 3, 4, 5, 6. Okay, then the probability was 1 over 6, 1 over 6, 1 over I'm talking about PMF. Okay, you should not confuse PMF with CDF. Okay, PMF is the pointwise probability. So pointwise probability was just 1 over 6, 1 over 6, 1 over 6. Okay, and otherwise it was defined to be 0, right? So it was like this. Okay, and it was like this, and there is no value taken here, and then it is like discrete values. Okay, we cannot join these points, right? Because this is PMF. Okay, and then for other 7, 8, 9, it is defined to be 0. Okay, so these are like discrete values. So if you see the continuous analog of uniform, then the difference is that we join this, right? Because it's a continuous, because x is taking the continuous values. So it looks like this in the continuous case. So discrete, and this is the discrete PMF, and this is the continuous PDF. Okay, so there is a relation between that, and the height of this is 1 divided by b minus a, where b and a were your given interval. Okay, so that's the plot of the PDF. So what are the properties of PDF? Since PDF is the derivative of the CDF, we have this. Okay, so this do you remember this? What is the relation between the derivative and antiderivative? Derivative and antiderivative. Okay, so so remember that if I have so f x small x, this is the derivative of the capital X. In other words, I can obtain capital X by integrating the derivative of that. Okay, so that comes from calculus. Okay, so that's how we relate the derivative and the integral, right? So in other words, if I take a derivative of this, then I will get back, so d by dx of fx x is f small x x. Remember, this gets substituted here because after integration, this becomes a function of, remember this whole thing is a function of x. Okay, so this is the relationship we know, okay, from calculus. So in other words, if a PDF is given, then I can always obtain the CDF by doing the integral. Okay. Okay. So and the usual results that we had was probability that a less than x less than equal to b, and that we knew that this is how it's defined. And in the case of continuous, we just have to do the integral like this, okay, from a to b, because this is minus infinity to b. Okay, so according to the definition here, if I put b is x here, x is equal to b, then it will be minus infinity to b and fx u du, and then we have fx a. So this is minus infinity to a, and then fx u du, right? So so what does this become, right? So then from the integration, you can recall that let us say a and b are some interval somewhere. Let us say a and b are somewhere here. So what we are saying here, and let us say a is less than b. Okay, so what we are saying is like we integrate from minus infinity to b. So minus infinity to b is here, and so we subtract. So it's like area under the curve from minus infinity to b. So let us say this is the area under the curve from minus infinity to b, and then you are saying subtract fx u du up to a. So this is the minus infinity to a range. So this is the area up to here. Okay, so this is the area up to here. So if I subtract, then the remaining area is this. Okay, so this remaining area will become a b fx u du. Okay, so this is coming from the calculus. Okay, so this is equal to this. So if someone asks me to compute the probability between A and B, then it's very easy for me to compute. If the PDF is given, then I can just integrate the PDF from A to B. Another thing to note is that minus infinity to infinity, if I do an integration of my fx of the PDF, then it is supposed to be 1. And that is also clear because this is the same thing as saying I'm computing probability from minus infinity x less than equal to minus infinity. Okay, so this is like all of the sample space. This is equal to sample space. Okay, so probability of a sample space is 1 by axiom of probability. Okay, so this is how we can claim this. Okay, so integration of PDF is 1, and the analog for this for the PMF was, if you recall, that PMF was px x, let us say small p, then sum over all x. Okay, this was 1. Okay, so PMF sums to 1, and same thing is here. In this case, the sum is replaced by the integral. The properties of the PDF is are the following: like fx x is greater than or equal to 0 for all x. Okay, and this comes from the fact that it's the derivative of fx x is the derivative of a non-decreasing function. Okay, non-decreasing function, which is CDF, right? So CDF is a non-decreasing because it's a cumulative thing. So as the x increases, the CDF will always accumulate more and more. So since fx is the derivative of a CDF, assuming differentiability here, then hence the derivative will be positive. Okay, because we know that the derivative of an increasing function is positive, because limit of derivative df by dx is defined to be limit epsilon tends to 0 f of x plus epsilon minus f of x by epsilon. So let us say we define derivative like this, then this is greater than this, right? So since f is increasing, or non-decreasing. Okay, so we have f of x plus epsilon minus f of x is greater than equal to 0 because this is increasing. Okay, and epsilon is greater than 0. Okay, so epsilon is greater than 0, so this thing is greater than equal to 0. Okay, so that's how we define that for an increasing function the derivative must be, so this is greater than equal to 0 here, epsilon. So it must be greater than equal to 0. Okay, you can also take for points. Remember that role of x doesn't matter. X can be also on the negative side. It doesn't matter. Okay, x can be some negative number. What really matters is like the epsilon and we are looking in future on the right side, right? So this is like f of x plus epsilon and then divide minus f of x, and then we are taking the ratio. So it's increasing as x is going to the right. Okay, so that's why we always have greater than equal to 0. It doesn't matter whether x was on the negative side, positive side, it doesn't matter. Okay, because it is increasing, so this difference will always be greater than equal to 0, hence the derivative must be greater than equal to 0. Okay, and fxx being the derivative of the CDF, which is a non-decreasing function, if it was strictly increasing, then it would have been greater than 0. But we know that CDF may not be strictly increasing because CDF does get flat after some point. So this is not strictly increasing. Okay, so hence it's greater than or equal to 0. Okay, so beyond the point here, fxx will be 0 because the derivative of CDF is flat here, so it will be 0. So integration of this is 1. We already discussed this above, and then we already discussed this. We are just noting down the points, and we can also define it for some set in general, for some set. Okay, so for probability that x belongs to A, it will be integral over A. Okay, so probability that x belongs to A is integral over A, and A can be like something arbitrary. It does not have to be like continuous interval. It could be from here to here and from here to here, like A, B, and then C, D. Okay, and this is your CDF. Then usually if you so my set A is the union of, let us say, A, B union C, D. Okay, so I may want to compute what is the probability that x is in A. Okay, so it could be either in A, B, or it could be in C, D. Okay, they are disjoint and so on. So in that case, I can do integral by integral on these intervals. We know that, right? So I can compute integrals between here, and I can compute integrals between here and here. Okay, so you can do it on arbitrary sets. In other words, if the interval is 0, 1, and 3, 4, then if I have to compute probability that x is in A, then it will be between 0, 1, and this will be between 3 and 4. Okay, so this is the second interval, 3 and 4. So let us see an example of PDF and CDF. We saw it for uniform distributions, but let us see some arbitrary thing. Okay, so let us say PDF is given by this. So this is the PDF of the random variable x is given by this, x greater than equal to 0. Then this is constant times e to the minus x, and otherwise it's 0. Okay, so it will look so here it's 0. And for x greater than equal to 0, so it is behaving like c e to the minus x. So it's going like this. For x greater than equal to 0, it's defined for all x greater than equal to 0. So this is how the PDF will look like. Okay. So the question is, what is C here? Find the CDF of x. Find the CDF of x. Okay, and find the probability that x lies between 1 and 3. Okay, so how are we going to find C? Okay, so which property here will help me find the constant C? Can you tell me in the chat? So which property will help me find the constant C? Property 2, exactly, Prince. Yeah, thanks. So property 2 will help us because we know that the sum of the PDF must be equal to 1 and limits are there. So property 2 will give us find the CDF of x. Well, CDF of x, we have to like integrate it over Yeah, we have to integrate it. So to find CDF, what was the rule? Fx x was minus infinity to x, okay, and f and the CDF, right? So fx and you treat this as a function of u so that you don't mix this with this variable which is inside, okay? After integration, it will become a function of x, but to not mix this x with this x, because limits, these are limits and these are the variable, okay, so they have to be a little different, okay, to avoid confusion here. So CDF we can find because PDF is given, we have to do the integration like this, okay, and find the probability that x is greater than 1 and less than 3, okay. So this will be the integral, right? So probability that x 1 less than x less than 3. So we recall from the previous, so this is like a, this is like b, okay. So and then we can do the integration a to b, so it's like 1 3 of the CDF, I mean the PDF, okay. So I can do, now I can write xx because there is no ambiguity because limits are not x, right? So I have to integrate like this. So let us do this this example anyway, like just for completeness. So the first question was find C, okay. So find C. So to find C, we know that, so we know that that minus infinity to infinity fx u du is 1, okay. So that's like property 2, like you said, and then this will be 0 to infinity c e to the minus u du. So we have just substituted fxu here, okay, and this will be c of minus e to the minus minus e to the minus u, and then 0 to infinity. So if you compute this, then it will be c only, okay. So so this implies that c is equal to 1, okay. So this is the first one, and then the second question was to find the CDF of x. CDF of x, so we know that this is fx which is minus infinity to x. So this is like PDF of u du, okay. And for x less than 0, for x less than 0, we know that that the PDF was defined to be 0 because that was the otherwise case, right? So this implies x will be 0, okay. So for x greater than equal to 0, for x greater than equal to 0, we have fxx. Here we can define, because minus infinity up to 0, it's anyway 0. So we ignore those cases and take only from 0 to x. So this will be e minus u du, okay, and this will be 1 minus e to the minus x if you integrate this. So from here we can say that, so this implies that we can wrap up this by writing it nicely. So this is 1 minus e to the minus x for x greater than equal to 0 and 0 otherwise, okay. So this is 0 otherwise. So this is the CDF of x. Now the question 3 was, or the question C was, probability that 1 less than x less than 3. So in this case, remember that we have both in hand. So we have both CDF and PDF. So we know that we can compute probabilities by using either of these. So let us say we use CDF. So using CDF, we can compute the probability that 1 less than x less than 3 to be, remember this is like fx 3 minus fx 1, okay. So that's how we define this, and this is this will come out to be 1 minus e to the minus 3 and then minus 1 minus e to the minus 1. Okay, this is the CDF that is given here, and that is what we are using here. So we can leave it here. So we got it, okay. And so equally using PDF, we can also compute. In PDF, we need to do the integral. So this is like 1 less than x less than 3. So this will be, the limits will be a, b, right? So 1 minus e to the minus 3 plus 1 minus e to the minus 3. So this will be 1 minus e to the minus 3 plus 1 minus e to the minus 3. So this will be 1 minus e to the minus 3 plus 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 1 minus e to the minus 3, and then here we will put the PDF. So this will be like some fx dx. Okay, so we know that the PDF of this was and c turned out to be 1, right? So so this is like 1, 3, and here we had c and e to the minus x dx. C was 1, so this was 1 here. So this comes out to be 1, 3, e to the minus x dx. Well, this is integration of this is minus e to the minus x and then 1, 3. Okay, so this is like e to the minus 1 minus e to the minus 3. So that's the answer. Okay, so we know with this example how it can be useful to compute. Now I can define something called range. Well, range, we don't have to define range. We have already done range, but assume that the range of a random variable is the set of all possible values. Not necessarily assume, but this is how it's defined. And then we can define range of continuous random variable. Okay, so we can define range in a way that we are only worried about the points where fx is greater than 0. Okay, it's like these are the only cases where probability is like positive and it's worth talking about. So we may define the range to be only the positive values that the PDF is taking. Okay, that's what we are saying. So recall that the expected value of a discrete random variable was this x times PMF of x. Okay, remember? And then if we replace the sum by the integral and the PMF by the PDF, then we get the expected value for the continuous case. Okay, so this over the continuous case, you replace sum by the integral, okay, and PDF by the CDF. PMF by PDF. Okay, so that's how you get expected value for for a continuous random variable. Okay, that's how we get the expected value of continuous random variable. So let us consider an example where x is uniform, okay, and uniform on AB, and what is the expectance of expected value of x? Well, in this case, we know that the PDF was given by 1 by b minus a. So we computed this before, x less than b, and it is 0 for x less than a or x greater than b. So that's what we know. The PDF of x is this. Now the expected value of x, now it's easy to compute. We know that expected value of x is defined to be minus infinity to infinity. X PDF of x dx. So this is now minus infinity to infinity. If we see minus infinity to a is 0 and b to infinity is 0. Okay, so is 0. So we can ignore these okay, and we can keep it AB. Okay, because minus infinity to a the integral was 0 and b to infinity integral is 0. So those we removed and we are only focused on now AB. Okay, so this is 1 by PDF, which is this 1 by b minus a in AB, right? So this is b minus a and then dx. So if we integrate this, then 1 by b minus a comes out, and in the inside we have x squared by 2, the integration of x, and this is AB, and this is turns out to be, after calculation, this turns out to be a plus b by 2. Okay, because this is like b square minus a, which is b plus a, b minus a, b minus a, b minus a gets cancelled. Okay, so that's how we have the how we compute the expected value. So we will do more on the expected value, PDF, CDF, and so on in the next class. Okay, so okay, then with that I will say bye and have a nice day. Grades of your quiz will be sent in within an hour or so. Okay, okay then. So thanks. Bye.